Second part of kinetics, we're going to be looking at activation energy. All right, so if we were to graph out the energy that is needed for a reaction to happen, it would kind of look like this. So our y-axis, potential energy, x-axis, reaction progress. Reactants, products. Okay, so as the reaction progresses, we're going to have this uphill battle with energy. So if we were to draw a line going directly across from where the reactants are at on the potential energy axis in the hump and measure that, that would be the activation energy. How much energy is needed for the reaction to take place? Now, as we go up the hill, if we were to kind of look at what's happening to the reactants, we would notice that things are changing. And at the top, this is considered to be a transition state because it is transitioning from reactants to products. Then after the hill, so on the downward slope of the hill, we go down, that energy, that potential energy is released, or it could stay up here. Now, since the products are way lower than where the reactants are at, this is telling us that this reaction is exothermic. If the products were higher than the reactants, then it would be endothermic. And the displacement between where the reactants are at and where the products are at, that is our change in energy between reactants and products. All right, so with activation energy, the rate constant depends on the magnitude of activation energy. Generally, the lower the value of the activation energy is, the larger the rate constant and the faster the reaction. So if there's a huge hump, the reaction is going to be slow. If it's a small hump, the reaction is going to be fast. We can actually calculate out what is the activation energy for a reaction by using the Arrhenius equation. Now, the Arrhenius equation, K is equal to A, capital A, times E, which that is a calculator function, raised to negative E of A over RT. Okay, so in this case, R is going to be 8.314 joules per mole times Kelvin. A is a frequency factor. That is a constant. Don't worry about it, okay? You won't be able to really find a number for it. So to derive this equation, once again, we're going to have to take some data from a reaction run a couple different times. If we take the natural log of K1 over K2 is equal to our activation energy over R times the inverse of T2 minus the inverse of T1. So let me go get my calculator real quickly and let's look at an example of that. Okay, so it says from the data below, calculate the activation energy for the reaction and what the value of the rate constant at 400 Kelvin. So once we find the activation energy, we can do the second part. This is a two-part problem. So first, finding activation energy, E of A. So what we're going to do is we're just going to take 2 points and plug in the data into our formula. So what I'm going to just do, I'm going to be lazy. I'm going to use first 2 points. Okay, so this is going to be 1 and that's going to be 2. So natural log K1, 2.52 times 10 to the negative fifth per second over 5.25 times 10 to the negative fifth per second is equal to E of A over R, 8.314 joules per mole times Kelvin times the inverse of our temperatures. Now, take note, the unit that the temperature is in for here is in degrees Celsius. And the R value, the unit for temperature, is in Kelvin. So we're going to need to convert our two temperatures from Celsius to Kelvin. Alright, so this is T2, sorry, hear my dog. 273.15 plus 298.9, 472.05 Kelvin. Now T1, 273.15 plus 189.7, 273.15 plus 189.7, 462.85 Kelvin. Sally. Alright, so that's where we're... So 1 over 472.05 Kelvin minus 1 over 462.85 Kelvin. I can't write right now. Here, let me... Sally, quiet. Okay, so let's plug all this stuff. Sally. Alright, so let's kind of clean this stuff up. Let's see what natural log of 2.52 times 10 to the negative fifth divided by 5.25 times 10 to the negative fifth. Sally! Let's say 0.734 is equal to E of A over 8.314 joules per mole times Kelvin times, now our inverse, so I'm going to take 472.05 minus 462.85 and that comes out to be a negative 4.211 times 10 to the negative fifth per Kelvin. Stop. Now. Okay, so now we need to get E of A by itself. Enough. Alright. So let's get E of A by itself. So activation energy would equal to negative 0.734 times 8.314 joules per mole times Kelvin divided by the negative 4.211 times 10 to the negative fifth per Kelvin. So let's see, negative 0.734 times 8.314 divided by negative 4.211 times 10 to the negative fifth. Okay, so the activation energy is 1.45 times 10 to the fifth joules per mole. So that's just the first part. Now the second part, what would the value of the rate constant at 430 Kelvin? So for that one, once again, we just need to pick another, or actually no, we're going to go up to Arrhenius equation and use that. And like I said, A, we're not going to worry about it because it's a constant and it doesn't really give you a number for it. It's just constant. Alright, so K is equal to, and I'm going to just take that A out, E raised to negative 1.45 times 10 to the 5th joules per mole all over 8.314 joules per mole times Kelvin times our temperature, which was given to us as 430 Kelvin. Alright, e to the negative 1.45 times 10 to the 5th divided by 8.314 times 430. And I'm coming up with 2.43 times 10 to the negative 18th. And K should come out to be per second. Or K should just be, yeah. Now we could probably put it into our equation up here as well if we just take in one of the data points, doesn't matter which one it is, and go from there. Now 430 Kelvin, let's kind of see where that's going to fall at on temperature. So 430 minus 273.15, that's 156.8 degrees Celsius. And if we kind of look, you know, our first temperature was at 189.7 and it was 2.52 times 10 to the negative 5th. And as our temperature goes up, K gets bigger. So since 430 Kelvin is a smaller temperature, the K should be smaller than what we see up here. All right, then the last thing is, you know, if a reaction takes place in multi-step part, kind of like, you know, what we're looking with Hess's law, one of the reactions is going to be a fast reaction, one of the reactions is going to be a slow reaction. And if we need to figure out or determine what the rate determining step is, we always go with the slow reaction. All right, so for this first one, our first reaction is the slow reaction, the second one is the fast. So the first one is the rate determining step. So the rate determining step, rate is equal to K times, now we look at our reactants because that's what we look at for this. We have NO2 plus NO2. So we can take K times NO2 squared. Excuse me. Now if we want to find out what is the overall reaction, and it's kind of like what we're doing with Hess's law. If we have something on both the left-hand side and the right-hand side, we can cancel those things out. Now, something that is made in the first reaction and then immediately used up in the second one, that is called an intermediate. And that can't be a part of the rate determining step, because it won't be there in the situation. So canceling things out, so NO3 gonna be gone, and one of our NO2s. So the overall reaction would be NO2 gas plus CO gas yields to NO gas plus CO2 gas. All right, so let's kind of look at this one. You're right. We have the decomposition of nitrous oxide into O, and it's a two-step mechanism. First thing, write the overall reaction. Two, write the rate law for the overall reaction. Okay, so part A, what is the overall reaction? Well, our intermediate is oxygen. So that's the only thing that we have to really take out. Now we have NO2O, NO2O. So we have 2 N2O gas. You'll see then over on the right hand side we have 2 nitrogen, so 2 N2 gas plus O2 gas. So that's the overall reaction. Now B, write the rate law. As I said, the rate law, or the rate law is the rate determining step, and that we use the slow reaction for that. So in this case, our first reaction is the slow reaction, so rate would be equal to K times concentration of N2O. And that's it. Now, what if we had the slow reaction as the second reaction? Well, if that's the case, then the first reaction would be fast, true, but it would also be at equilibrium. Okay, now if it's at equilibrium, then we have two K's. We have K1, which would be for the forward reaction, and K to the negative 1, which would be the reverse reaction. So for this one, we could say that rate is equal to K of 1 times concentration of NO times concentration of Br2, and that's equal to K negative 1 times concentration of NOBr2. Because in the reverse reaction, the only reactant would be, in this first one, is the NOBr2. So if we need to figure out, the rate of the reaction, and since our second reaction is the slower one, rate would be equal to K times, or K2 times NOBr2 times concentration of NO. Now, we do need to bring in the information from our first reaction, the fast reaction. We only do this when the slow reaction is the second one, because if we look, we have NOBr2 in both of them. So if we get, from the first reaction, if we get NOBr2 by itself, okay, concentration of NOBr2 would equal to K of 1 over K of negative 1 times concentration of NO times concentration of Br2. And we're going to plug that in to our rate determining step, or the rate of the reaction formula from our second reaction. So rate would be equal to K of 2 times K of 1 over K of negative 1, and concentration of NO times concentration of Br2 times concentration of NO. Okay, now we have concentration of NO in there 2 times. So K of 2, K of 1 over K of negative 1, concentration of NO squared times concentration of Br2. Now the reason why we put that squared is because since we have both NOs. So this video should help you with the second part of the assignment that I posted and everything. If you have any questions, please email me, and I will talk to you later. Thanks for watching.